Okay, so previously we talked about how derivatives are rates of change. Now we're going to look at some applications of that. And we are momentarily jumping out of Chapter 3 and into Chapter 4, but we will go back and get sections 9 and 10 of Chapter 3 later. So, best way to learn this is just to work through some examples. That's what we're going to do. First up, we've got a 13-foot ladder leans against a wall. The bottom of the ladder is 5 feet from the wall and slides away from the wall at a rate of 3 feet per second. How fast is the top of the ladder moving down the wall? When you're dealing with these problems, best thing to do at first is just draw a picture of it and label it. So we'll draw a picture of our scenario. We've got the wall, the ground, draw a little ladder, and then we'll label things. So I'll switch colors for that. I'm going to label that I know that this ladder is 13 feet long. It's always 13 feet long, that doesn't change. And we'll label this distance here as x, and we'll label this distance here as y. I changed colors because those quantities are going to change. And just to be explicit, we can go ahead and write down what are x and y. So x is the horizontal distance from the base of the ladder to the wall, and y is the vertical distance from the top of the ladder to the ground. And again, I'll make a little note over here that green means changes with time. So we know the quantities that we're most interested here are x and y because they're what is changing. So we need to write an equation that relates x and y. We see that there's kind of a triangle going on, right? Got x, y, and the 13-foot ladder. So the Pythagorean theorem tells us x squared plus y squared equals 13 squared. Again, that's the Pythagorean theorem. We're going to see that in this section, our geometry skills are going to become important. We're going to need to know some formulas for areas and things like that. So now we have an equation. We want to differentiate the equation with respect to time. Remember, x and y change as time changes, so x and y are implicit functions of t. So here's where that taking derivatives of implicit functions section is going to come in handy. So our derivative is 2x dx dt plus 2y dy dt. And that derivative of 13 squared is just a 0. So next step, stop and ask, what do we know and what do we want to know? we know that x is equal to 5 because the ladder starts 5 feet away from the wall. We know that dx dt is equal to 3. So it says the ladder slides away at a rate of 3 feet per second. And we know that x squared plus y squared is 13 squared. We can rewrite that and solve for y, and it tells us that y is equal to the square root of 13 squared minus x squared. So we said that x is 5, so 13 squared minus 5 squared is equal to the square root of 144. That gives us 12. So we know that y is 12. And what we want to know dy dt. We want to know how fast the ladder is going down the wall. So next up, we just substitute and solve. And that's my dog. So our equation up here, 2x dx dt plus 2y dy dt equals 0, that's what we're substituting into. We're going to solve it for dy dt. So we get 2 times 5 times 3 plus 2 times 12 times dy dt. That's all equal to 0. So we can rewrite this 30 plus 24 dy dt is equal to 0. 24 dy dt is equal to negative 30. So that gives us dy dt is equal to negative 30 over 24, or negative 5/4 if you want to simplify. And lastly, we would like to put that back in context and answer our original question. So in context, the ladder is moving down the wall at a rate of 1.25 feet per second. So we saw when we got our answer it was negative. That is what tells us that the ladder is moving down the wall, not up the wall. And negative 5/4, 5/4 is 1.25. And we knew our units were feet per second. So that was our first example. Next up, we've got an example about a pebble. So a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So small circles, and they get bigger as they go out. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area, which we're going to call A, of the disturbed water changing? So again, let's start off by drawing a picture of it. So I've got my ripples. And here's my radius r. So remember, radius is just half of the diameter of those circles. So we've made a picture, we've labeled it. Now we need to find an equation that relates A, the area of the circle, to r, the radius of the circle. And like I said, this is where our geometry skills are going to come in handy. The area of a circle is equal to pi r squared. So we've got A equals pi r squared. And now we need to differentiate that equation with respect to time. So we get, well, first we need to think about which of these is changing as time changes. Well, the area of the circle is changing as time changes. Pi is not. Pi is just a mathematical constant, and the radius is changing. So we know that we're going to need an extra piece there when we differentiate A and when we differentiate R. So derivative of A is just 1 times dA dt. Derivative of pi r squared is 2 pi r dr dt. Next up, what do we know and what do we want to know? What do we know? Well, let's see. It tells us that we're interested in what's happening when the radius is equal to 4 and when the radius is increasing, so that's dr dt, at a constant rate of 1. So we know r and we know dr dt. What do we want to know? We want to know dA dt. We want to know how the area of the circle is changing. So it's time to substitute and solve. So we're interested in finding dA dt. Don't have anything to substitute there yet. That's 2 pi r, which we know is 4, times dr dt, which we know is 1. So that gives us 8 pi. Put it back in context. The total area of disturbed water is changing at a rate of 8 pi feet, per second. Now there are 2 more examples, but before we do those, we're just going to pause and write down what is our general strategy when we encounter one of these problems. So our general strategy is this. First, we want to draw and label a picture. Then we want to ask ourselves what quantities are changing and what quantities are constant. That'll come in handy when we start taking derivatives. Then we want to write an equation that relates the variables. We want to differentiate that equation. With respect to time. And then we again ask ourselves something. So this time we ask, what do we know? And what do we want to know? And then lastly, we substitute and solve. And put things back in context. So there are two more examples here, and what I would recommend is that you actually pause this video, read the example, try to do it yourself, and then watch me work on it. So just like we practice things in class, you get into groups, work on things, and then we go over it, that's what we're going to do here too. Just going to do it at a distance. So this next example, a rocket that is launched vertically is tracked by a radar station located on the ground 3 miles from the launch site. What is the vertical speed of the rocket at the instant that its distance from the radar station is 5 miles, and this distance is increasing at a rate of 5,000 miles per hour? Again, start off by drawing a picture. So here's my wonderful picture of a rocket. And we know that this rocket is some distance off the ground. We also know that it's some distance away from a radar station. And notice we've kind of got three separate distances here, right? We've got this vertical distance, this horizontal distance, and this diagonal distance. So now we want to label things. So this vertical distance, we're going to call that y. So it's the rocket's vertical distance from the ground. We'll make a note of that. And now we're going to label this distance z. So we're going to call this the rocket's distance from the radar people walking by outside again. And we see that there's a radar station located on the ground 3 miles from the launch site, so this horizontal distance, that's 3. So now we need a relationship so let's see. Well, again, we've got a triangle, so our relationship is 3 squared plus y squared equals z squared. And we can take the derivative of that. So differentiate with respect to time. And that gives us, well, let's see, derivative of 3 squared is 0, derivative of y squared is 2y dy dt, derivative of z squared, 2z dz dt. Easy enough derivative. Next up, what do we know? Well, we know that we're interested in what's going on when the rocket is 5 miles away from the radar station and when it's getting farther away at a rate of 5,000 miles an hour. We also know y squared plus 9 is equal to z squared. And we know that z is 5, so that's y squared plus 9 is equal to 25. Y squared is equal to 16, so y is 4 miles. And we want to know dy dt. So we're interested in how the rocket's vertical distance is changing. Now we substitute and solve. So we have 2 times y, which is 4, times dy dt, which we don't know yet, is equal to 2 times z, which we're saying is 5, and dz dt, which is 5,000. So that gives us 8 times dy dt is equal to 50,000, which means dy dt is equal to 6,250, and the units on that are miles per hour. Putting things back in context, the vertical speed of the rocket is 6,250 miles per hour. And technically, at the instant that the rocket is 5 miles from the radar station. That brings us to our last example here. Again, I would urge you to pause the video here, read the example, and try it on your own before you see my solution. So hopefully you paused. Welcome back. With this example, we've got a balloon. So a spherical balloon is being inflated so that its volume is increasing at the rate of 5 cubic meters per minute. At what rate is the diameter increasing when the diameter is 12 meters? And here we've got a little hint to remember what the volume of a sphere is. First up, we draw a picture. And let's see, what are we interested in? Well, we're interested in the diameter. So, not interested in just the radius this time. We're interested in actually that entire distance there. We're also interested in the volume, but we can't really draw that. So we've got d, which is equal to the diameter of the balloon. We have V, which is equal to the volume of the balloon. And we have R, which is equal to the radius of the balloon. We're not really interested in the radius, and we haven't labeled it on our picture, but we do know that there's a relationship between the radius and the diameter, and our equation currently only has the radius in it, so we're going to need to kind of switch some things around. So next up, what is the relationship? Well, starts out, it's that volume is 4/3 pi r cubed. And we know that the radius is half of the diameter, so we can rewrite this as 4/3 pi d over 2 cubed, which gives us 4 over 24, or 1/6 pi d cubed. Because remember, we're interested in diameter. So next, we want to differentiate with respect to time. So let's see. Derivative of v is just 1, and it's changing with respect to time, so it means it's 1 times dv dt, which is just dv dt. We've got 4/3 pi r cubed. Well, that's going to give us a 3r squared dr dt. So we can kind of move some things around here. Ah, my bad. Wrong equation. Let's start over. So our equation is actually 1/6 d cubed. V is equal to 1/6 d cubed. So we do have a dv dt on the left. And over here we have 1/6 pi times 3d squared dd dt. So remember, we're interested in the diameter, not the radius. So then we can move some things around here, so we get 1/2 pi d squared dd dt. And what do we know? Well, we know dv dt is equal to 5 at the time that d is equal to 12. And what do we want to know? Well, we want to know dd dt. We want to know how the diameter is changing. So next up, substitute and solve. So 5 is equal to 1/2 times 12 squared times dd dt. So 5 is equal to 144, there's a pi in there. So 5 is equal to 1/2 12 squared times pi times dd dt. Or I'll move that pi in the middle there. Well, we'll make it even more clear. We'll say pi over 2. So 5 is equal to pi over 2 times 12 squared times dd dt. So 5 is equal to 144 over 2 times pi times dd dt. So moving things around, we get dd dt is equal to 10 divided by 144 pi, which is about 0.022. The units on that are cubic meters per minute. So not centimeters, cubic meters. Yes, just wanted to check that that really was cubic meters. So, lastly, just need to put some things in context. So in context, the diameter of the balloon is increasing at a rate of 0.022 cubic meters per minute. So that's section 4.6. There will also be some exercises on Moodle for you to try. You've survived your first video. Thank you for putting up with this. And let me know if